Joris van der Bosche, talking about GeoPandas, and Joris has been involved with pandas, GeoPandas, Pyogrio. Yeah, why don't I just let you introduce yourself? Take it away.
Yeah, thank you. It's based on my presentation from FOSS4G earlier this year, which is a longer presentation, but I will try to go a bit fast in some areas, and you can always ask questions afterwards. So I'm Joris van der Bosche. There is also another GeoPandas maintainer here, Martin Fleischmann. He should be here already, I think. So yeah, I'm at the moment mostly an open source software developer, mostly working around tabular data in Pandas, Apache Arrow, and then also in GeoPandas, so the geospatial interest is there. And in this presentation, I will give a very brief intro about GeoPandas. I assume that most people are somewhat familiar with it, and then I will mostly focus on some of the interesting developments that we have been working on with the team, and that might also be of interest for the Pangeo community. GeoPandas, for geospatial analysis in Python, of course, it's very broad. It's focused on vector data. It's to work with tabular data there, with vector geometries, combining the functionalities of different tools, combining pandas with Shapely, with PyProach and others. So, very brief introduction to GeoPandas. You have a table here. I'm reading a GeoJSON file. In this case, could also be a shapefile. And so you have a table where you typically have at least one, it can also be multiple, but column with your geometries, point, line, string, polygons, so the vector geometries, that's our geometry column, and some additional columns typically called like features, or the attributes, properties of your features. And it's based on pandas, so you have a pandas data frame. You can do all the things that you would be able to do with the pandas data frame, like doing some filter operation, calculating something. But we also provide all the functionality of Shapely on top of pandas. So, for example, calculating the distance of that, on all the geometries in your series, but also all other typical geospatial operations. And then there are also some other more advanced functionalities like spatial joins, overlays. Well, not necessarily advanced, but not just like element-wise spatial operations. So this is an example of a spatial join. I won't go into detail, but that's also one of the most used functions of GeoPandas, I think. In addition, we have interfaces to GDAL based like Fiona or pyogrio to read data, PyProach to work with projections, with Matplotlib for plotting, nowadays also with Folium for interactive web-based plotting, etc. I had some highlights of the last releases in my presentation, but I shortened this part a bit, just this list. So I already mentioned that we added an explore method to have a Folium leaflet-based basic visualization of your geometries. In addition to this standard spatial join, we now also have a spatial join based on the nearest, on proximity. We improved some IO related things, and a lot of bug fixes, etc., and small improvements. But for the rest of the presentation, I mostly want to focus a bit on some of the underlying parts of GeoPandas. So this is an overview of the most important technologies, or ecosystems libraries that GeoPandas is based on. So you have pandas, and then the geospatial or geo community with those three core libraries. And we have been working on improving the interfaces to geos, being Shapely, and the interface to GDAL, and especially to improve performance on those areas. And that's where I want to focus on for the next part. So how can we make GeoPandas faster? And then as a start, focusing on, in the end, Geos is the core of GeoPandas. It's the library that provides, on top of the table, functionality of pandas. It's Geos that provides all the geospatial functionality to work with your geometries, to perform overlays, predicates, all kinds of transformations, etc. So the library that we use is in GeoPandas is Shapely. Shapely has traditionally had a very nice Pythonic interface, but limited to single geometry. So you see here a small example of create a line point, a line string, calculate the buffer. We check like whether the polygon contains some other geometry. But Shapely itself was always like limited to this single object, while for GeoPandas purposes, also for, I think, integration with Xarray, we want to have arrays of objects of geometries. And specifically for pandas, we also want to add attributes to it. So if in a full table. And well, the attributes is what GeoPandas provides.
Getting these star files out there.
And the array, the limitation of not having an array is what we want to solve in Shapely 2.0. So that's what I'm presenting in the next slides is what is becoming Shapely 2.0. This is briefly showing how GeoPandas currently works. So we just basically store, an object D-type array, NumPy array of geometry. So if you do an operation like the distance operation, we literally do a Python loop through our geometries and call the equivalent Shapely method, which then calls into Geos, etc. So for fast operations that are optimized in Geos, you get a lot of Python overhead. So Shapely 2.0, it's already in the works for quite a while now. By now for a few years, and there is also the PyGeos package that's basically implemented this and is already being used for a few years. But we basically like copied the full of PyGeos into Shapely and refactored Shapely, the existing Python interface of Shapely on top of those new internals. What does it provide, Shapely 2.0? It's providing array based functions, so vectorized functions. That's the core improvement of Shapely 2.0. As I mentioned, it's merged in Shapely. We now have a C extension type, so it's implemented in C using the Python C API. A little bit of Cython, and so no longer the C types and no longer the dynamic loading of geos at runtime using C types. So it should also improve like installation issues, hopefully. All the existing APIs of Shapely still exist, but so the main part is that we have now element-wise functionality. So while before you might needed to do something like a list comprehension, a loop through all of your geometries, we now have top level functions like contains, where you can pass scalar or array arrays of geometries, and that will do this operation element-wise, vectorized. I have just to, because I think this part is quite essential, and or important for potential use cases here. So I created here a small array, 3 points. I created one polygon. So you can already see, I can check for all my points whether they are contained by the polygon, and you get a new NumPy array as a result. But I want to highlight that an important aspect of this is that those functions are actually NumPy ufunc. So that means that all the functionality that you know from NumPy, for example, broadcasting, that works also with arrays of geometries using and with the Shapely geospatial functions. So as a small example, like I could do the distance. If I would have 2 arrays of points, I could create the distance element-wise through those 2 arrays. And to show as an example, like the broadcasting, if I would want to have the pairwise distance of this array, I could, like with introducing the new axis to make it 2D, and here in the other direction. This will, broadcast those 2 arrays and automatically calculate all the distances between those 2 arrays of points. As a small, illustration of the fact that those functions are actually ufuncs, universal Python NumPy functions. That's very nice. It's a nice interface. It's also a lot faster. Here are 2 examples of contains operation, distance operation in like specific benchmark. But yeah, it's a lot faster. I won't go into detail here. Also for a spatial join. We also vectorized the spatial indexing based on the STR3, and there are some releasing the GDAL, so you can use it with Dask. I will quickly mention it later. So that are some of the other features here. I won't go into detail here, but there are some changes needed to make it more compatible with NumPy arrays. So the geometries are now like actual scalar objects. They are no longer something sequence-like. They also made hashable, so you can use it, for lookup based on just like the object itself, or you can use it in the pandas index. But the status, there is a Shapely beta 1 released, and there is an RC planned for next week. But yeah, it's certainly a big change. So also here the quick shout out to, if you're using Shapely, very welcome to test. The instructions are still for the alpha, but yeah, so now there is a beta and almost an RC. That was for Shapely. So I focused mostly on Shapely. I will very quickly, briefly mention some of the work that we have been doing on I/O. Related to GDAL and non-GDAL I/O. So for GDAL, the standard interface, like package that we have been using with GeoPandas is the Fiona library. But it's a bit a similar story as with Shapely. Fiona provides a nice interface, but it's also focused on an iterative interface where you like get one row at a time, where on the Python level, where for the purpose of GeoPandas, we want to read like a whole file at once into a table. We don't necessarily don't need this this file like interface of Fiona where you can iterate through the rows. So here we worked with some of the other GeoPandas developers on a new package which is called pyogrio. That is very much based on Fiona, but also provides like a vectorized I/O you can use it directly, or you can use it through the familiar pandas API using read file and specifying the engine pyogrio. And then if you use this, you will see that it's can give you a very nice speed up for reading large shapefiles, large geopackage files. So here is an example from a large geopackage file with building outlines from New Zealand. And yeah, you can see it's a lot faster and also more memory efficient. So that's quickly about pyogrio. There is a nice feature coming in GDAL 3.6, which is almost to be released. There is a release candidate for GDAL, for that version of GDAL. And GDAL has introduced a new API to get columnar data. Yeah, instead of getting each feature once at a time from your data sets, it has added an API based on arrow. So using the arrow memory layout to represent your columns of a table, to be able to access the data from a vector layer in GDAL directly as columnar data. So we don't have to do this conversion from row-wise data to columnar data on the Python side. That's something that is coming, and it will give another speed up for those typical reading those vector files. So that's another improvement here. That's for I/O based on GDAL. There is also some movement in some other formats, some new formats. GDAL actually already supports it as well, but you don't need GDAL to read those files, because there are other libraries that can efficiently read those files. And I'm talking about GeoParquet. I won't go into detail here neither, but so Parquet is an existing file format that is widely used in data lakes and things like that, originally from the Hadoop ecosystem. So it's columnar binary formats, highly optimized for small storage. So it's used a lot for tables. We have tables with geometries, so we decided to get together from some people from different projects to agree on how are we going to store geospatial data in this existing file format. And that's basically what GeoParquet has become, just like some agreement on metadata, how to store geospatial data. So currently using well-known binary, but we are planning to expand on that, and like the current reference system, etc. So that's wanted to mention this as well as a nice improvement in the ecosystem when it comes to file format specifically for vector data. I will go through this. A last thing. So I talked a bit about speeding up GeoPandas itself, making it faster, the geospatial operations with Shapely, faster I/O. But there is also the next step. How can we use more than a single core, as the currently Pandas and GeoPandas still does? So we have also worked on a bridge with Dask. I think the concept of this is very familiar for people in Pangeo, because you work a lot with Xarray and Dask. It's backed by Dask. So it's very similar to, I'm going to skip this part. So the Dask data frame consisting of smaller pandas data frames. So the GeoPandas Dask bridge is basically exactly the same. Our dask-geopandas geodata frame is a subclass of the Dask data frame, where each of its partitions consists of a GeoPandas geodata frame instead of a pandas data frame. So in the same way as dask data frame is extending pandas data frames, the dask-geopandas project is extending or scaling up the GeoPandas geodata frame. So it's also very similar as dask data frame, providing an API that is familiar for people already using GeoPandas. And we implemented most of the element-wise geospatial operations in dask-geopandas already. So all the element-wise operations are available. Since starting with Shapely 2.0, which releases the GIL, you can actually make use of multi-threading also on your single core for those operations. We also have a basic spatial join. We don't yet have an overlay, parallel overlay. That's something we certainly want to work on in the future, but that's not yet available. This basic support for spatial partitioning, meaning that each partition in the dask data frame can have its own spatial extent, and that this information is used to determine, for example, if you do a spatial join, to know which partitions of the left data frame and the right data frame need to be combined when you're joining them spatially. So yeah, I think I will leave it at this, and so we have some room for discussion and questions.
All right, thank you so much, Joris. Julius, you can turn off the recording.